AI training is now one of the largest capital expenses for modern technology companies. We invest hundreds of millions of dollars into GPUs, but those GPUs only create value when they are actively training models. It's the corporate equivalent of having a world class factory sitting idle because delivery trucks are stuck in congestion. One of the biggest choke points in large scale AI training is data I/O, or data input output. When people talk about training huge state of the art LLMs across thousands of powerful GPUs, they always focus on compute, the petaflops, the exaflops, the horsepower. But what's emerging is that a training run will only be as fast as the lowest point on its most chaotic part. And that chaotic part is always the IO pipeline. You've got GPUs demanding intensely bursty chunks of data right away. And the whole goal is to somehow convert that jagged demand into a flat, steady, reliable flow from storage. And look, we get it. Stability is everything. If you're running a 2 month long training job and it's costing millions of dollars in compute time, any stall, even one that lasts just a few milliseconds, means your most precious metric, MFU, or model flop utilization, collapses. And that cost just compounds, and it compounds fast. So we need an architecture that takes a fundamentally unstable process and just makes it rock solid and steady. But first, let's understand where this digital chaos comes from, why LLM training is so unstable, and then think of a multi-layered solution, explaining exactly how it could turn that chaos into a flatline, predictable system. We need to step back and start with the chaos itself. I mean, what's so counterintuitive is that despite all this computational power, the IO load is not a nice even stream, not even a little bit. It generates huge sudden spikes. I mean, you'd assume a massive parallel process would be predictable, like a giant river just flowing steadily. But it tends to have all these flash floods. Why all these flash floods? Because the whole system runs on synchronization. And synchronization means everyone has to start the race at the exact same time. So the first cause of a really predictable spike is the start of an epoch. A new epoch means a huge data refetch right after a shuffle. So if you have 5,000 GPUs and all 5,000 GPUs need new data slices at the exact same millisecond, you're going to have a huge spike. That's a predictable traffic jam. Everyone's trying to hit the refresh button at the same time. And then you get these follow on smaller but equally disruptive spikes when you hit batch boundaries. Every single computational rank requests the next piece of data at the same time. Think of it like a train leaving the station. Every car in that train needs the signal to go, and they all ask for it together. And the worst peak, the most problematic one that comes from the synchronization points, are the global barriers. Global barriers create the most chaotic event. A global barrier is just a point where, say, 1,000 GPUs all have to synchronize their state before they can move on. And when they're released from that barrier, they all simultaneously hammer the storage together to pull that next chunk of data. It's a digital pylon, and it just stresses the backend to its breaking point. So we have predictable floods from the epochs, minor jolts at the batches, and then these catastrophic tsunamis with the global barriers. But there's something more adding even more. So even if 999 out of 1,000 GPUs are perfectly in sync, you'll always have a few random or maybe just one straggler, a few late ranks, and that finish a tiny bit behind. And as soon as those stragglers finish, they create these smaller, unpredictable mini bursts that hit the system right when they're trying to recover. And it's like a tiny aftershock that causes the final failure. And what's emerging is that the storage infrastructure, the big centralized object storage, That's just inherently terrible at dealing with these sudden peaks. Storage, object storage, wasn't designed for this. It's completely ill-equipped for this purpose. Object storage was designed for massive scale, sure, and for reliability, but it wasn't designed for microsecond predictability under these kinds of loads. It has these slow tail latencies, meaning 1% of your requests take forever. It has fixed throughput ceilings, hard limits on requests per second, and an awful noisy neighbor effect where one job spike can destabilize every other job in that whole cluster. And the outcome is this brutal visualization you see in the charts below, that jagged line of IO demand, which peaks and then crashes. Peaks, crashes the system, and then it slowly recovers only to crash again moments later when the next barrier hits. It creates that oscillation, fast, then stall, then recover, then stall again. And MFU just crashes every time. The amount of wasted time, wasted cycles, wasted money, it's staggering. So let's try and ground this in a simpler concept before we dive into the management layers that could solve these problems. Let's think of the training process as a massive, super high-end restaurant kitchen. Think of the GPUs as hungry, high-paying customers and the centralized object storage as the main pantry full of ingredients. So in a chaotic state, imagine 1,000 customers bursting through the door and shouting their orders all at once to the chef. The kitchen will just collapse and the whole system will grind to a halt. What's needed is a management system that stops the kitchen from ever seeing that chaos. So here comes the first layer that we need in this first line of defense. Layer 1 is the distributed NVMe high-speed storage buffer. This is basically like putting a dedicated high-speed warming drawer right next to the every single chef. So instead of the chef having to go to the kitchen to get all their ingredients, there's a local shelf, a warming shelf with most commonly requested ingredients. It's this local shelf acts like a shock absorber for the compute node itself. So how does this local buffer actually hide the latency? It completely changes the relationship between the GPU and the storage. I mean, the GPU is still going to request data in these huge sudden bursts. That demand doesn't change. But the new management system fetches the data from the main pantry, the object storage, continuously at a smooth, stable, predetermined rate. So the GPUs are demanding data, but the local NVMe is absorbing that difference. The local NVMe is the intermediary. So if the GPU suddenly needs, say, 128 samples instantaneously, a massive burst, it just pulls them from the fast local buffer, which is kept full. And if the remote storage takes, say, 5 milliseconds longer than expected to deliver the next chunk, the local buffer hides the latency completely. The GPU sees instant service, and the remote pantry just sees a smooth, steady restocking request. So that solves the local GPU problem. It stabilizes one GPU's experience. But what if all 5,000 GPUs start their smooth, steady restocking requests at the exact same time? We still have a collective burst hitting the backend. So while we have solved the local problem, we still have a global problem. We need to stop the nodes from collectively overwhelming the object storage, and that is why layer 2 is so critical. Layer 2 is the token bucket IO credits, which is a concept borrowed straight from networking from traffic shaping. This is the ultimate traffic cop, and it's so effective because it gives you a guaranteed control over the collective volume. Every node accumulates IO credits at a fixed rate, let's say 2 gigabytes per second. When a node reads data, it consumes credits. If you run out of credits, you simply cannot place another order on the main object storage. You have to wait. It's like the rule in our restaurant that says a waiter can only send 2 orders per minute back to the main kitchen. no matter how many people are shouting at them. It physically prevents the system from accidentally unleashing a, 50 gigabyte per second surge and just slamming the object storage all at once. So it's like a guaranteed throttle. It ensures the object storage backend only sees a smooth, flat load. It never exceeds that fixed safe rate, even if the nodes internally want exponentially more. So we fix the timing with layer 1, and we fix the collective volume with layer 2. The output of layer 2 is a smooth pipe, but we still need to talk about the quality of what's flowing through that pipe. We are rate limiting the volume, but what if the messages that we are sending are super tiny and inefficient? Now that leads us straight into layer 3, or adaptive batching of back-end reads. This solves the efficiency problem. LLMs often request data as many, many small objects, millions of little shards. And if those went straight to the backend, you'd generate millions of individual GET calls. And the problem with these millions of tiny requests isn't just the sheer number, it's the metadata involved. Every single small request needs negotiation, authentication, tracking. It's a huge metadata overhead. And it causes massive bursts in requests per second, and that's a whole different kind of a spike. It's not a data spike, it's a management spike. So if you convert 1 million tiny handshakes into one firm agreement, you just slash that overhead. So what we need is a consolidator that collects all these small incoming GPU requests from the nodes and it groups them into one large optimal size batch before it ever hits the storage backend. Now, converting millions of these small chaotic reads into a single efficient large sequential read is what's going to take effect and result in a smooth request from the kitchen or the backend object storage. The ending cite examples of batching reads, and that's a game changer for backend stability. It cuts down the metadata load and flattens those request spikes. You're maximizing throughput by making the requests, chunky but happy. Okay, so now we've built up 3 fantastic layers of defense. But we still have a looming issue, which is scalability under peak demand. If we have, let's say, 1,000 GPUs all demanding the same one popular piece of data, we still have a problem. Because even if that one piece of popular data is buffered locally and batched efficiently, that one local NVMe buffer on that one node hosting the data can still get overwhelmed, especially during those global barriers. So now we have a scalability challenge. And this brings us to layer 4, or dynamic striping across caching nodes. We have to parallelize access to the data across many NVMEs, not just the one that physically holds it. Though we build a distributed caching fabric, the NVMEs stop being these isolated local stores and they start acting as one massive shared buffer pool. That's the innovation. The system makes sure that node A can now read data directly from node B's NVMe without ever going back to the slow central storage. And more importantly, the batches are prefetched and stored as striped replicas across this whole network. So, in our restaurant analogy, this isn't just having a warming drawer. It's about making sure all the warming drawers in the entire restaurant are synced up and can serve the same popular dish. So now imagine 500 GPUs all request the most popular data shard, which happens at every batch boundary. Without striping, the one node holding that data gets hammered. It instantly bottlenecks the entire 5,000 GPU cluster. But with dynamic striping, the load is automatically spread out. So instead of one node collapsing, maybe 20 or 50 nodes all share that responsibility. So each node only has to serve a tiny fraction of that peak demand. You eliminate the single point of collapse. So this is the architectural secret to managing that collective synchronization without crashing the whole thing. Which brings us to layer 5. And this feels almost like an insurance policy. But maybe it's the most crucial element for guaranteeing absolutely zero stalls. Deep prefetch queues. This is the system that ensures you never ever run out of runway. It's not reactive, it's intensely proactive. It doesn't just fetch the next batch, it fetches multiple future batches, and it maintains this deep rolling queue of data that's constantly ahead of what the GPU is demanding. If you try and stay 30 to 90 seconds ahead of the GPU and pipeline, not just a few 3 to 4 seconds, then the tail latency problem that we spoke about at the start can be managed. Because the 30 to 90-second buffer is the ultimate defense shield. It's for the unpredictable worst case scenario. So even if one request hits a massive metadata spike, or the network gets some jitter, or the object storage gets a catastrophic 50 milliseconds to respond, the training pipeline does not stall because the data it needs for the next minute is already there. It's waiting, ready to go to the local NVMe queue. So while the GPU demand is intensely bursty, that jagged up and down pattern, the prefetch queue makes sure that the actual I/O pattern placed on the storage is flat and predictable. You're separating the demands with time. The prefetch system converts that bursty demand into a flat, continuous demand on the object storage, and it masks all the variability in between. So now let's zoom out and look at the combined effect with our restaurant analogy one last time, because it really solidifies the whole solution. Okay, so when we started, we had a chaotic restaurant, 1,000 customers ordering instantly, the kitchen collapsing, and the quality of service, the model flop utilization or MFU, was just oscillating all over the place. Now, with these 5 layers of management, the customers or the GPUs, they can still place their orders in bursts. But the main kitchen, the centralized object storage, it never sees that chaos. First, you have that large warm food buffer holding pre-cooked items. That's layer 1. And layer 5, the NVMe and the prefetch queue right next to the server. The customer gets their food instantly from that buffer, hiding any latency from the kitchen. Next, the orders are pulled into the kitchen at a fixed, steady cadence. That's layer 2, the token bucket. The kitchen is never overwhelmed. Third, instead of shouting millions of small, confused requests to the main pantry, the system bundles them into big, efficient orders. That's layer 3, adaptive batching. It makes the whole supply chain work. And crucially, when multiple servers or multiple GPUs request the same super popular item, they pull it from shared distributed shelves. That's layer 4, dynamic striping. They don't overwhelm one single pantry worker. And the result is that the kitchen works out is in a stable, predictable manner. The customers end up seeing instant service, and the MFU, or the efficiency of the whole operation, stays constant. It rises and then it stays high. That is the definition of turning digital chaos into foundational stability. So, what does all this mean for you? This architectural pivot, what does that mean for your AI training models? It means that it's not just about making things a little bit faster with faster GPUs. It's about making extreme scale AI training possible by turning chaotic I/O from a destabilizing liability into a predictable, manageable utility. By using this multi-layered I/O management system, the complexity is effectively pushed away from the centralized fragile storage backend where chaos causes these catastrophic crashes, and is moved to the distributed edge nodes where that complexity can be buffered and managed and controlled locally with fast environments. This is going to in turn end up saving you millions of dollars.